I now want to show you this third method in here of incorporating BRAM or memory cell into our code. Specifically, I'll show you how to force Vivado to use BRAM to describe its memory arrays or the RAM. And I'll show you three different examples, and the difference between them is subtle. So let me explain the differences between the three examples. So the first one, the one you see here in red, it's going to be synchronous dual port. And you will see that the word synchronous appear everywhere in here. And the reason why is because BRAM itself is synchronous. Remember, it's an ASIC on the FPGA board, and as it turns out, it's a synchronous memory type, and it's wrapped with some sort of circuitry. But anyway, going back to the topic in here, so I'm going to show you three different examples. So the first one has 2 ports. So this dual ports mean it's 2 ports. And really, it's the most generic of the three. So it has a port 1 and it has port 2 in here. And this port 1 can be read or write. Okay, you can do one of them. You can use it for read and you can use it for write, but you can only use it in one of the operations. And the second port, which is port 2, you can also use it for read and write. So this second one in here, this example in here, which says simple synchronous dual port. So it's also dual port. So we're going to have P1 and P2, but the difference is now one of them will be dedicated read and one of them will be dedicated write. So let's assume that port 1 is the read, the other one will be write, and you can't, like, port 1 is, that's it. You can use it for read only, not read or write. The last one I'm going to show you is a synchronous single port RAM, and it is just a single port RAM, so you don't have P1 and P2, you only have P, and that happened to be used for read or write, but you can't do both at the same time, you just have to decide it. Alright, so again, as it turns out, if I actually follow these particular templates or the code I'm about to show you, Vivado somehow understands that that code should be interpreted and implemented on BRAM or like using BRAM. But before I show you the code, I just want to mention that most of the code that you see now, or you're going to see in the next few minutes, is all imported from here, or it's based on the code that I've seen in this documentation. So let me show you that documentation. So this is Vivado's UG901. It's like there are different versions, but I'm using the 2018 version here. And if you go to the table of content, you're going to see that chapter 4 deals with HDL coding techniques. Specifically, you're going to see the way you describe memory. It is RAM HDL coding techniques, for example, or interfering ultra RAM. So for example, if I actually click on that here, I will get all sorts of information about the RAM and the BRAM and how we can use it. Okay, this is the template method that I showed you in there, but anyway, we're going to go in here, and at some point you're going to see that there are certain code examples, for example, a single port RAM with asynchronous read coding examples, and you get to see these. So somewhere in this documentation, you're going to see these templates I'm about to show you, or that I base my code on it. And as it turns out, Vivado is programmed in such a way that if it sees these templates, it will know to implement that particular memory array or RAM using BRAM. Okay, so let's start with this synchronous dual port RAM here. Okay, remember it has 2 ports, each one of them can be read or write, Okay, so here's a logic diagram of it. There's like some sort of a box diagram for it. So I made the first port in red and then the second port here in blue. And as you might expect, each one of them, because it can be used as read or write, it only need one address. I'm going to call it address A, and this has address B in here. And it will only need one write enable and one write enable in here. It'll have one data output and one data input, one data output and one data input, each one of the ports. And that's why you see here in these in this module. So in this module, I called it BRAM synchronous dual port. This is the most generic of the 3 examples I'm about to show you. It has a couple of write enables, a couple of addresses, one for A, one for B, a couple of the input. This is technically the write data. Okay, so I called it just DIN because it's just easier to comprehend here. So I have DIN A and D input B. Basically, DIN stands for input, and of course we have a couple of the outputs. All right, so let's go about it. Well, we're writing memory code, so the first thing we need to do is define that memory. So I'm going to do data with -1 in here, and then this is to 0, and I'm going to call it memory, and then this has to go from row 0 all the way to 2 to the power address with -1. Okay, this is how we define memory. Again, we go with the ports. Okay, so this one here has 2 ports, so let me just write the code for port A, and then I'll write the code for port B somewhere around here. All right, so again, everything is synchronous because we're dealing with BRAM. Okay, so the way we're going to do it is we're going to say always at positive edge of the clock. Okay, begin and an end, and in here, because it's synchronous, I'm going to say if write enable of A, I will say, well, memory at location or address underscore A should be equal to the input of A. And of course in here, we're going to do the following. Data A, which is actually some sort of a read data, will be memory, and that's address of A. All right, that's how we do for port A. How do we do port B? Well, it's exactly the same way. So we're going to do this here. We're going to copy this guy in here, and let me just fix this typo that it probably doesn't like. Let me just hover over it. It's telling me data A is not declared because I called it the out, not data A. So we're going to see this here as the out, and now I'm going to copy this. It really is exactly the same for port B here. But all we have to do is just shift these guys, or rename A to B, and rename A to B, and just rename A to B, and this is A to B. And now, if I actually go here to the Flow Navigator, and I actually say run the implementation so that we can see what does it actually implement, I will see that it will actually utilize the BRAM, not the lookup tables. So let's take a look at the RTL analysis while the implementation is actually running. And as you can imagine that I have, I believe I have the wrong one in here. So let's reload that. No, this is the correct one. And I do see some sort of an error in here. The out B, it kind of implemented it as the out using the out A. So let me just correct that error in here. Let me show you. So believe it's here. It's probably because I didn't change one of the addresses in here. You see, I didn't assign it to the output B. This is port B, so I just forgot to do that. So let's do reload in here, and it will know to connect the out B. All right, now taking a look at this implementation, as we expected, it implemented it well. It's interpreting it as an RTL RAM, and it has a couple of synchronous output, the output A and the output B. And I have a couple of write enable, a couple of addresses, one for A, one for B, and a couple of the input in here. And it actually figured out that you'll see that this is write address 4, read address 1 and 2, and so forth. It actually figured out it's a dual port memory. The implementation is still running, but I just wanted to show you that the synthesis here figured out that this is using, it's not using lookup tables, it's not using flip-flops, it's using half of a BRAM. And half of the BRAM makes sense. Let's take a look in here. So we have that one here is dual port. So we decided that the address width is 10 and the data width is that. It's 2 to the power 10 is actually 1024 times 8. That means it's about 8 kilobits. And we know that the BRAM can be split into two 18 kilobits. So using half a BRAM makes sense. The implementation also confirms this is actually using half a BRAM. I'm not using lookup tables. I'm not using flip-flops. And another comment in here, if you deviate a little bit from this template that I showed you here and here, I don't remember these templates, by the way. I'm just seeing in here, they're written in front of me in Note. I just wanted to show you like in progression how I actually write that code. But really, in reality, what I do is I actually take a look at the code that I already wrote and I just copy and paste it, because a little bit of deviation, for example, taking this D out outside the always statement and making it an asynchronous, this will mess up this usage of the BRAM. Vivado might not know that I intend to use BRAM because it's outside the template. So following this template exactly will help you a lot, just utilizing the BRAM and freeing up the lookup table so that you can actually do some sort of a logic. However, if you need to use something else, for example, or you need some other functionality, what I would recommend is you take that, whatever BRAM template that you end up using, I would just instantiate it in a different file and just wrap that circuit or that instance with something else that I want to do. But I wouldn't change the code here itself. The only thing I would change is a parameter, but I can do it while I'm doing the instantiation, of course. Let's take a look at that utilization report in here. Of course, we did see the half a BRAM, but I just want to show you also with the utilization report what we can get in here. So let's take a look in here. So if you take a look at the summary, for example, it tells you I am using, well, it was showing the wrong one, so I had to reload it. It was showing the older one, or something that I ran before. So now it's showing the right one. Let me just see the utilization report one more time in here. All right, so we can take a look at the summary, and the summary tells me that your total utilization is half a VRAM. I'm not using any flip-flops or anything else, and you can see it in here. It's actually block RAM tile, and it's about 1% or something like that. You're using half of a VRAM. All right, so let's move on and actually write another code for this simple synchronous dual port RAM. It's still another, again, it will have 2 ports, P1 and P2, but one of them will be read and one of them will be write. So each port will be dedicated. And I'll base my code in this one here because it's really, really similar. So I'll just copy this here, at least up to here, okay? And then I'm gonna say BRAM and I'm gonna call it simple. And simple is just because it's going to be a dedicated BRAM in here, or a dedicated port. So let's take a look at the schematics of this. Now I don't have an A and B anymore. There's no need to keep A and B, so I'll just have a read address and a write address and a D in and a D out, and that's it. So I'll basically use the memory definition as before. I don't have a couple, well, I do have a couple of ports, but really I can combine them within a single always statement. I'm just going to remove this guy from here, and I'm going to tell you if it's write enable, I'll just say, well, the memory at address of the write in here will take the data in, okay? And if I have the data out, for example, will be assigned whatever in memory and address are. And I believe I got everything I need at this point. Let's double check. So positive edge, remember everything has to be synchronous because we're using BRAM. So if write enable, I'm going to say the memory at address W. Of course, it will be the DN, and here the D out will be whatever we have the address R. And at this particular moment, I am done. I have a simple BRAM. It's actually dual port. It has a one read port here. You can specify the address read, and one write port in here. And of course we have a DN that is associated with the write, and we have a D out that is associated with the read. You can run the implementation and you can take a look at the utilization report, and you will see that it actually is utilizing BRAM because I'm following that template. All right, so last but not least, I will show you how to write a synchronous single port RAM. So the single port RAM is actually very similar to the dual RAM. It just has one of these ports, not 2. So let me show you here. So what you do see in the following is I really took the dual port RAM, and I just put it here. You have one port, but it can be used to read or write. So technically this particular memory or RAM or memory array or register file, you can either read or write. You can't do both at the same time because you only have one single port. So how do we go about this? Well, I'm just going to copy and paste that code from the dual port RAM, and really all you have to do is just remove port B and you're technically done. And I kept it as write A and address A and D in A and D out A in here just for the sake of simplicity, so that I can just do this here and just remove it and I'll be done. Again, if I run the implementation, I guarantee you're going to see that the utilization report will show me that I'm only using BRAM.